Let's get started. Lecture 18. How did shear and moment diagrams for point loads go? Hopefully that was easy. I'm hoping it was. Okay, good. I'm still working on grading exams. My goal is Wednesday. Absolute worst case scenario Friday, but I'm not letting it go later than that because I need to get them off my desk. Homework 5.1 is graded. So everything outstanding should be good to go. 5.2, that was the one that was due today. So hopefully, again, that went well. 5.3 is going to be due on Wednesday. Today, we're going to look at shear and moment diagrams for uniformly distributed loads, so loadings like this. On Wednesday, we're going to be looking at triangular loads. And we're going to be using, deriving some equations, and we're going to plot them. So on Wednesday, I would bring a laptop if you can. Okay, it's not absolutely necessary, but it would be kind of nice to have one if you did, or if you could, because we're going to plot them using Excel. So bring one if you can. Okay, did everybody get the code? I'm seeing Mr. Shakarov. He's like, I'm not going to say no, but I'm going to see if he notices that I haven't gotten the code yet. Mr. Foster, everybody else got the code? Okay. All right. Ooh. Scroll on my mouse kind of went nuts there. Okay. All right. Like I said, our goal. What our goal is to take. Sort of my teaching philosophy is to take the topic, start out easy, and just ratchet it up a little bit so that we fully understand it. And so we'll just, we started off with concentrated loads, which I think was very straightforward, and now we'll just ratchet it up just a little bit, okay? Now we are still using the same principle, the idea that in order to go from the loads to the shears, that we are essentially integrating the load diagram, as it were, in order to get the shear diagram, and then we are integrating the shear diagram in order to generate the moment diagram, okay? Now, like I said, we're not going to be computing integrals directly in a lot of our problems, but I do think it's kind of nice to just have this in the back of our head for the purposes of a concept, because I think that conceptually this can help us understand what we're doing and why we're doing it. Okay? Remember that between load and shear, at any given point, the slope of the shear diagram is equal to the load because the derivative of slope is load, and then between 2 points, the change in shear is equal to the magnitude of load between those 2 points, because that's all this is saying. And then the flip side over here. Now, our goal today is to talk about distributed loads, but let's just do some basic calculations here. Let's just sort of walk this through in our head. Okay, so let's say that I had a beam, something like this, uniform distributed load, and let's put a number on this. Let's say that this beam had -5 kips per foot. And hold on, maybe I'll put it like, actually, let me take a step back. I think I went a little too far ahead there. Let's say it's 5 kips per foot distributed load. Now I propose that the function that we're going to use to represent that load is going to be -5. Now why am I proposing that? Because if I draw like a y-axis here and an x-axis here, I propose that the 5 kips per foot is going down, right? So this is going to be negative. Okay, with me so far? So if I were to try and come up with a function for the shear diagram, how would I do that? I would have to integrate that, right? I'd have to integrate -5. Okay? What is the integral of -5? -5x, right? Wrong. It is -5x plus c. So we'll call it plus c1 because we're going to have another one. But don't forget that arbitrary constant of integration. And in here, there actually is a value to that constant of integration. Okay? We'll see that later. We're going to figure out how to come up with these, but we're going to do it in a little bit of a roundabout way. But it's not 0. There actually is a value there. Okay? So if I wanted to determine the moment diagram, okay, what I would do is I would integrate this. So I would integrate that. Okay? And so what is the integral of that? What is the integral of negative 5x?
Negative 5 over 2x squared.
Negative 5 over 2
X squared.
X squared.
Plus C1x.
And then another constant of integration, which we'll call C2. Does that make sense? Okay, so here I have a function for the shear, and here I have a function for moment. So let's just think about like plotting this, what this would look like. So if I were to plot the shear, what would it look like? I mean, what does the graph of something like this look like? Linear, but which way? This, like this, right? So it would look something like that, right? The slope would be -5, right? What would this point be? Whatever C1 is, right? Don't get worked up with, what is C1? I'm just, y'all get the idea that this is going to be a line trending downward with a negative slope. The slope is equal to the load, so on and so forth, right? So what is the plot of this going to look like? Like if I were to plot that, what would it look like? A parabola, right? That x squared term means parabola, okay? Now, let me ask you this. Is it going to look like this, or is it going to look like that, left or right? Right. Why? Because the x squared term is negative. So this moment function might look something like that, right? Okay? Starting to see where the idea of the shapes are coming from? See, I propose that, so now let's sort of focus on the slide a little bit. So I propose that if you have a constant load, that is going to generate a linear shear diagram. The slope of that shear diagram is going to be equal to the load, and we're going to go from maybe a high shear to a low shear. And if we take the integral of this shape, the area under this curve is going to equal the change in moment from one side here to another side here. And so how do we tie this to this, and how do we tie it to the parabola? Here we have a high shear to a low shear. So I propose we have a high slope to a low slope. Does that make sense? So for example, whenever the shear diagram is 0, the parabola should be flat, right? That's where the maximum or minimum of that parabola is going to be. In most cases, I guess, in structural analysis, a maximum. Does that make sense? Everybody with me on the idea? Okay. Now, in order to... Now let's ignore the calculus a little bit. Let's just get back to some basic fundamentals. We're going to be dealing with some geometry problems in some of the examples that we're going to do. And what I don't want to happen is I don't want you to fully understand the structural analysis but fail at a challenge like this. So if I give you a shear diagram that goes from 25 kips to negative 75 kips, what's the area of this and the area of that? It's a very simple question, but I don't want that to inhibit the overall exercise. So I want to do this problem sort of on the side. So let's say that we have 25 kips to negative 75, and I want to determine the area here and here. How do I determine the area of this triangle? How do I determine the area of a triangle in general? A half of base times height. For both of these triangles, I know what the height is, right? this is 25, this is 75, or negative 75. But I don't know what the base is, right? So maybe the start would be to figure out what these bases are, okay? And I guess my question is there an easy way of doing that? I propose to you, yes, there is an easy way of doing that, okay? Let's start off with a simple question. A simple question might be, what is the slope of that line, okay? Well, I propose the slope of that line, we can just sort of deal with that as like a change in y over a change in x, okay? Now, how we would do that for this problem is we would say, okay, we go from 25 kips to negative 75 kips, and we do that from 0 feet to 25 feet. And so that's going to be 100 kips over minus 25 feet, or negative 4 kips per foot. Now, for this example, we had to do that calculation. Are we really going to have to do that calculation in most structural analysis problems? No, because this slope is just going to be equal to whatever this load is. So we had to do that for this calculation, but we shouldn't have to do that for most structural analysis problems. So far, so good? Okay. So here's what I propose, okay? I propose that if slope is the change in y over the change in x, then the change in x is just going to be the change in y over the slope. Actually, let's do it like this. Okay? That's how I propose we're going to do this. Okay? So what do I mean by that? How do I determine this distance right here? Let's do this in green. How do I determine this distance? And we'll call it x1. I propose that x1 is just going to be 25 kips over 4 kips per foot, which is just going to be what? 25 over 4, so that's 12 and a half over 2. What is that, 6.25 feet?
Yeah.
And then maybe x2. And we'll just use absolute values here. And what is that? Is that 18.75? Do these two numbers independently make sense? I mean, what happens if you add them up? What do you get? 25, right? So if I want to determine area 1, 1/2 base times height is what? And then maybe we'll call this area 2. And then area 2. And then this is negative 75. We'll keep that negative since it's below the line there. And I think this one comes out to be something like, what is it, negative 703? Okay. Does that make sense? Does that idea make sense? I hope so. I hope that's not terribly challenging, what we're doing here. My point is I don't want this to be a distraction from our overall goal. I don't want this to be the hard part. But so I think it's valuable to sort of take a step back and go, wait a minute, is everybody okay with this? All right. Sound good? All right. So if that's the case, or I'll just use the notebook. Okay. If that's the case, then let's look at this problem here. Okay? So I want to draw the shear and moment diagram for this problem. And notice how I'm not giving you the reactions, because I want to go through the exercise of computing these reactions. Okay? I want to go through the exercise of doing that. Okay, and I've thrown distributed loads and point loads on the problem. Okay, so basically taking what we did last time and again just ratcheting it up just a little bit. Okay, now I've got two reactions here. I'm going to assume that those reactions are vertical. Spoiler alert, they both are, but you know, again, if we made a wrong assumption, we could easily fix that. Let's see about computing these reactions. Now I'm going to try and maybe squunch my reaction calculations a little bit over here on the right, because I kind of want to have everything all in one spot for visual purposes. Okay. All right. So first thing, let's just all recognize are we all okay with that? Hopefully. Okay. Let's handle this the way that we've handled any problem so far. So what do you want to do? Some moments at A to determine the reaction at C, and then some verticals to get the reaction at A. Okay? Okay. Now, before we start writing something down, I want to make a really, really important point. Okay? Let's talk about this distributed load. So we're computing reactions right now. We're not drawing the shear moment diagram. We're just computing reactions. I want you to tell me how you would handle that distributed load. What would you do?
Take the area and place it at the center.
Okay, so you're going to collapse it into a point load. What is that point load going to be?
180 kips at 30 feet.
Okay, so that's going to be something about like this. Okay. All right. That's right. Nothing wrong with that for the purposes of computing reactions. But I want to be clear that while that is statically equivalent for the load as a whole, that is not equivalent for the purposes of constructing a shear and moment diagram. I mean, look, that's 180,000 pounds. If we're talking about bending the beam, what's going to be a worst case scenario? Taking that 180,000 pounds, lumping it all right in the middle, or taking that 180,000 pounds and spreading it over 60 feet? Which is going to be a worst case scenario for the beam? The first one, right? Okay. So we are doing this for the purposes of constructing or computing support reactions. When we construct a shear and moment diagram, we need to ignore this. This doesn't exist. Okay? And I'll emphasize that when we get to that point, but let's just take it one step at a time. Okay. So I've got 180 kips times 30 feet, right? What are my, this is going to be 30 kips times what?
40 feet.
60 kips times what?
80 feet.
80 feet. And then CY times 40 on the other end. Or CY times 60, sorry. Okay. Bless you. Okay. Okay. All right. So 180 times 30 I think that's 5,400. This is 1,200. This is 4,800. So I think that sums out to what, 11,400? So what's CY?
190.
Everybody okay with that? So maybe what I'll do is I'll say maybe I'll just do that just to sort of make the point that I've computed that. Rocking and rolling. So now what we'll do is we'll sum forces in the vertical direction. Oh, that jumped away from me there. Oh, 60. So we've just got AY and this reaction here going up, these three going down. Hopefully I'm not doing this part too fast. Hopefully this is easy, right? So $30 and $60 is $90, $90 and $180 makes $270. And so this is $80 kips. Okay. Let's do that. In case everybody still needs to do some writing. Okay. All right. Let's take a step back here. Is everybody with me so far? Everybody comfortable with what we're doing so far? Very good? Okay. Any questions? All right, I'm going to do something that I want to make sure is very crystal clear. My next task is to construct the shear and moment diagram. Okay? See this 180 kips? I'm going to get rid of it. Now you can leave it there on your notes if you want, but I'm getting rid of it. And I'm going to tell you why I'm getting rid of it. Because I'm constructing the shear and moment diagram, which is a plot of the change in vertical forces and the change of moments on the beam as the loads are. Okay? That idealization, that 180 kip collapse that I just did, that was an analytical tool that I used to compute support reactions. When constructing the shear and moment diagram, it's not going to work. And a good example of why is, remember the section cuts? Remember how I said if you cut a section and look to the left, you can't use the same collapsed load, right? You got to recalculate it. Y'all remember that? Well, what are you doing when you construct a shear and moment diagram? You're cutting an infinite number of sections. Every time you cut a section and look to the left, cut a section, look to the left, cut a section, look to the left, you get a different load. You can't just use that 180 kips, okay? So we use that as a tool to compute support reactions, and now I want to forget about it, okay? Sound good? All right, so what I'm going to do, if it's okay, is I'm going to take all these calculations and let's try this again. I'm going to take these calculations, I'm going to just scooch them just a little bit. Scooch them just a tad. just so I got a little bit of room here as I construct this moment diagram. I just don't want that to get in the way. Or shear moment diagram, I just didn't want that to get in the way. Okay. All right. So just as before, we're going to draw those little guidelines down. Bless you.
Thank you.
It's that time, isn't it? Okay, so we'll draw these little guidelines down. And then we're going to strike a solid line. And we're going to say that this is, put my label over here on the left. Doesn't really matter if it's on the left or on the right. And then we'll do this. Okay. All right. So we'll start at 0, and then hopefully we'll end at 0. Okay? Now, somebody tell me what's the first thing I need to do. Go up 80. Okay? So we'll draw us a line, something about like this. All right. Now let's talk about what happens from point A to point B. Let's just keep our discussion simple. Am I going to go up from point A to point B, or am I going to go down? We'll go down because the load is pointing downwards, right? How much load exists between point A and point B?
3 times 40.
3 times 40 or 120, right? So there's 120 kips. So if I'm at 80 here, where should I be here? Negative 40. Now, so if I'm at 80 and I should be at negative 40, what does the shape look like from here to here? A lot. We're all saying the same thing. So it should look something about like that. Remember how I said straight edges would help? So that's what my shear diagram looks like from A to B. Okay. Let's give myself a little bit more room down here because I have a feeling I might need it. Okay. Tell me what to do now. If I'm at negative 40, what do I do? Go down 30. So if I'm at 40, negative 40, go down 30, what's that put me at? Negative 70. So we'll drop down like that. What happens between B and C? Say it again. 320. Well, hold on. How much? Well, 3 times 20, right?
3 times 20.
That's it. 3 times 20 is 60, right? So if I'm at negative 60 and I drop down, or if I'm at negative 70 and I drop down 60, what's that put me at? Negative 130. And that's going to be at the same slope, right? Because this line and this line need to be at the same slope because it's the same load. Bless you. So now what happens? Boo! Big old jump up, right? So if I'm at negative 130 and I jump up 190, what does that put me at? 60. So that's going to be now what happens from C to D? Horizontal, right? Because there's no load between C and D. And that brings me back down to 0. And that, ladies and gentlemen, is your shear diagram. Trickier than the last time, but I think my real point is that it's not that tricky, you know? It really shouldn't be. It should be pretty straightforward, okay? How are we doing so far with this idea? Making sense so far? Okay, okay. All right, let's, so we've got a shear diagram. The next step would be to plot the moment diagram. Now how, if we have a shear value, or if we have a shear diagram, how do we get from the shear diagram to the moment diagram? We integrate, right? So let's start integrating this, and let's do it right to left. Like let's start over here and work my way over, because I think the math gets easier or harder as you go this way. What's the area under this part right here? What's the area? It's
1,200.
60 high, 12 or 20 across, so 1,200, and I'll call that positive. Okay. Now, I'm going to do something over here on the side. Let's take a look at this region right here. So, watch this. So I'm going to not worry about the negatives. I'm just going to say 130. And that dimension is 20. From high school geometry, do you remember what we would call that shape?
Trapezoid.
A trapezoid. Does anybody remember how to compute the area of a trapezoid?
Average pH.
There we go. So what we can do is take the average of 70 and 130, multiply it by this. Because what we're essentially doing is we're saying, okay, I can do better than that. That's better. Because what we're basically saying is that we can take this little bit, stick it over here, and then it's just a rectangle, right? So we can compute the area as 20 times the average of those two. Does that make sense? Now, if you want, you could break it up into rectangles and triangles. That's fine too. However you want to do it. It doesn't really matter. But what I will do is I will put a note right here, and I will say and I think I can do this in my head. 70 plus 130 over 2 is 100 times 20. This is negative 2,000. Okay? So far, so good? Okay. Now, the fun part. These triangles. It's like I knew this geometric problem was going to show up or something. It's crazy, right? We got to compute the area of this and the area of this. Man, it's like I knew this was going to happen or something. Whew. All right. So, by the way, what's the slope of that line?
3.
Well, not 3, but yeah, negative 3. But you're right, 3, from a magnitude perspective.
About 3.
So, how do we compute that distance?
It's 80 over 3.
80 over 3. So 80 over 3, or 26.67 feet. Here, I'm going to move that. I'll label that somewhere else. And that's going to be 40 over 3, right? So somebody help me out. What is the area of this big triangle right here? 1/2 base times height. And I don't think the decimals work out very nicely. It'll be like 0.666 or 333, whatever.
1066.666.
We'll call it like that, 1066.67. And by the way, what's this one?
Negative 266.67.
Negative 266.67. Okay. By the way, what happens when I add up all those areas? What do I get? What is 1066.67 minus 266.67 minus 2,000 plus 1,200?
Should be 0.
Should be 0. Is it 0? Yes, it is, right? So here's the point, right? Why does the shear diagram start at 0 and end at 0? Because the sum of the forces in the y direction are 0. Why do the areas add up to 0? Because the sum of moments are 0. That's what that means, okay? Does that make sense? Okay. Okay. So far, so good? Okay. Now, let's drag this down a little bit. Now I'm going to show you something, okay? I dragged this line, this line, this line, this line down. Those are the same 4 that I drew before. But I'm also going to draw a new one. I'm going to draw a new one right there, okay? I'm drawing a new one right here because this is where the shear equals 0, okay? So that's a new one that didn't exist before, so that's why that's there. Okay. So we already know that the moment diagram is going to start at 0 and end at 0 because the area is balanced. Like, we already know that's going to happen. So all we got to do now is just figure out what it looks like from point to point. Now, before I start drawing something, let's see if we can figure out just magnitudes. Okay. So before we figure out the shape, from here to here, I'm going to increase, right? How much am I going to increase? 1066.67? So I'm going to that's where I should be. What about from here to here? I'm going to drop down, aren't I? And how much am I going to drop down to? If I'm at 1066.67 and I drop down this much, what's that going to put me at? 800, right? So okay. And I'm at 800, I drop down 2,000, that's going to put me at what? Negative 1,200. And then I'm at negative 1,200, jump up 1,200 to bring me back to 0. Sound good? Okay. Now, here's my question. Okay, so this is 0, and this is what? 1066.67. Here's my question. Is it going to look like option 1? Or is it going to look like option 2? 1, right? 1, because negative parabola, right? Now, if you want a simple sort of like mnemonic that I sometimes remember, okay, do you see how the shear diagram goes from a lot of shear to a little shear? Like a lot to a little. Y'all see that? Lot to a little. So if the shear goes from a lot to a little, then the slope goes from a lot to a little. Do you see that? So lot to a little, lot to a little. And then little to a lot, little to a lot. In fact, this is all one parabola, okay? So you're testing my plotting skills a little bit, but that's that parabola right there. So what happens from 800 to 1200, or from 800 to negative 1200? We just have a new parabola, okay? So this 800, negative 1200, do we go option 1, option 2? 2, right? So it's just going to do this. Okay? Let me see if I can do a little better on that. And, by the way, what does this look like? What does this look like?
Line.
It's a line. Constant shear, linear moment. And that's your moment diagram. Okay? So what I'll do is I'll say quadratic, quadratic, and that's linear. Just to sort of make the point that it's quadratic. Now, sometimes I've gotten questions about, like, what is actually going on at this point 800? Because my math skills my plotting skills, my artistic skills are probably not the greatest. So what's happening at that 800 from a math perspective is you're getting two different parabolas. So this is a piecewise function. So we have like one moment function that goes from here to here, and then another moment function that continues. And what's the difference? So I'll do my best to sort of illustrate that. So if you want me to sort of like zoom in on that, okay? So what's happening is we've got one parabola that's going here, and then we have another parabola that's going like that. And what is the difference between the two? Right here, I propose the slope of that line is minus 40. And then for the other parabola, we get a sudden change in slope. And that sudden change in slope goes from minus 40 to minus 70. Now, how did I come up with the minus 40 and the minus 70? Because that's what's happening with the shears, right? The slope of the moment diagram is equal to the shear, right? And so right here, we're getting a sudden jump in shear, so we're getting a sudden change in slope. That's what's happening. They're both parabolas. They're just different functions for that very reason. Okay? Does that make sense? So if my art was a little off, or my plotting skills were a little off, that's what's going on. What do you think? Any questions? Does that sound good? All right. I've got you some more practice problems for this. I'm going to clean up my notes on this in between classes, but that's all I have for everybody. Don't forget, next time, bring a laptop because we're going to use some Excel plotting. That's all I got, everybody. I will see you all on Wednesday.